All right, hello everyone. I'm Netanel Lindner. I'm a professor of theoretical physics at the Technion, and I'm also the CTO and co-founder of Qedma. And today I want to introduce our software product QESEM. QESEM stands for Quantum Error Suppression and Error Mitigation. In Hebrew, QESEM means magic. I hope it will live up to this expectation. And QESEM is a software that's basically geared to giving you reliable and accurate executions of quantum circuits on large scales. And I will first, give some theoretical background on error mitigation and the motivation for using error mitigation for quantum computation. This is kind of completely general background. And then I'll kind of dive deeper into our specific product. I'll describe the workflow. I'll show large-scale demonstrations we did with this software, and also discuss kind of some of the inner workings, the key innovations that are behind this software product. Also describe something which I think is very promising, is a method to combine QPU and HPC resources using QESEM in order to basically allow a hybrid classical quantum execution of workflows using classical tensor network approaches. And then for an outlook, I'll both describe how error mitigation can be combined together with error correction to really push the boundaries of what's possible with quantum computers, and also give kind of much more near-term prospects for when we could expect to have quantum advantage using error mitigation with quantum computers that we have today. So let me set the stage. So we're dealing here with the problem of errors. Errors are, I think we all agree, these are like the main obstacle for executing quantum programs and getting something practical out of them. If you ever have any experience with running quantum programs on actual QPUs, you know that you have a signal which decays exponentially with the size of the circuit. We'll call it the volume of the circuit usually. And this leads, even with the best fidelities you could find today on any QPU, anything more than a few hundred gates would lead to a severe systematic error in the result you're getting. Now, there's two kind of approaches to remedy this. One of them we've heard about a lot yesterday with some beautiful talks, error correction. So error correction, has very stringent requirements. It requires both very high gate fidelities, but also it requires a large overhead in terms of the number of qubits it needs in order to encode quantum information. On today's QPUs, error correction is not practical yet, and even once it becomes practical, it would not be able to correct errors to an arbitrary level, just because the number of qubits that we'll have will be finite. The other approach to dealing with errors is error mitigation. Error mitigation uses different resources to deal with the errors, and that's just increasing the runtime. However, with error mitigation, at least in its most basic form, you don't need to use any extra number of qubits. So one physical qubit is just one logical qubit for error mitigation. Of course, you have to be very careful and have an efficient method to perform your error mitigation, otherwise your runtime is going to be extremely prohibitive. And I think what's the most promising is basically once error correction becomes practical on some level, it allows to reduce the errors by some amount. You can now combine error mitigation and error correction to really push the boundaries of what you can do, and also this allows you to relieve some of the very stringent conditions of error correction. So you'll be actually able to do error correction with less stringent requirement if you combine it together with error mitigation. So this is a very promising direction, and I'll discuss it a little bit toward the end of the talk. So if we want to look at this a little bit more quantitatively, we could ask ourselves, okay, what is the actual measure of complexity of a quantum circuit, both in terms of its classical computation complexity required to, for example, to simulate it, and also the complexity in terms of running it and mitigating the errors. So we discussed this notion of circuit volume. It needs to be refined a little bit. The actual quantity you're interested in something is called the active volume. This is the number of gates. Usually we're talking about 2-qubit gates because these are the main source of errors in most QPUs. So the number of 2-qubit gates affecting some observable you want to measure. Usually it has a form of a light cone for physicists that kind of think about this. Yes, and it could have more complicated forms for different circuit structures. If you think about this active volume and you set some accuracy that you require from your computation, say epsilon, this is the accuracy that you would want to get. The volume you're limited to, if you just run on the quantum computer as is basically epsilon over the infidelity. This is the maximal volume you can reach. Infidelity here is 1 minus the fidelity. And you can see this just by kind of expanding this to first order, this exponential decay to first order. Now, when you use error mitigation, and specifically when you use an unbiased form of error mitigation, meaning that you're guaranteed to have no systematic errors and only statistical errors, which are inherent in any quantum execution. It's just part of quantum mechanics. Then, as I'll show you in a second, you can go up to a circuit volume, which is, instead of this epsilon over the infidelity, which is some number which is the log of the overhead you're willing to pay in terms of QPU time. I'll discuss this in a more detail in a second, over the infidelity. And if you take the ratio of these two volumes, you get something we call the circuit volume boost, which is basically the factor by which you're able to enlarge the size of the quantum circuit you can execute. And this volume boost can be large. It can be large when you're demanding high accuracies, and it basically diverges as 1 over epsilon. To see this, let's kind of take a very, very simplistic model of error mitigation. I mean, you know that there's a couple of equations here, but I think we'll all be able to follow them. So the model for the QPU here is that every flop, basically every cycle, I'm throwing away all of the qubits with some probability, which is the infidelity here, and I'm replacing them by completely random qubits in a random state. And this leads to this exact exponential decay here, where this now becomes exact in this very non-realistic but insightful model. And when you also measure this observable on the QPU, you have this systematic error, and also this statistical error, which is just 1 over the number of shots you require. Okay, so this again shows you that if the volume you're limited to is epsilon over the infidelity, and also that you need the number of shots, which goes as 1 over epsilon squared. This is just statistics. Okay, so now how could we mitigate the effects of error here? Assuming that we somehow characterize the device very precisely, and we know the infidelity to very high precision, we could just rescale the measurement, okay, this measured value of the observable. We rescale it by this exponential factor, and then we recover the ideal signal, but with this inflated statistical error. Okay? So we see 2 things here already with this very simplistic model. One of them, in order to do the mitigation, we need a very accurate characterization of the infidelity, because if we get this wrong, we're going to multiply by a wrong exponential factor, and this is going to give us a very big systematic error. So we need very precise characterization. The other lesson we learn here is that we're inflating this statistical error, so the number of shots we need now needs to take care of this inflation here, and we'll need a number of shots which is exponentially larger than the original number of shots we needed on an ideal quantum computer. Okay? So if you now assume that you're willing to spend X times more shots to do error mitigation relative to what you'd want to spend on an ideal quantum computer. So this is your, your overhead for doing error mitigation, a multiplicative overhead. Then you see that the ratio between, as I said before, the ratio between the mitigated and the raw volume is going to be this log x over epsilon. So you see two things. First, you can already get very high volume boost, 1 over epsilon, with very moderate moderate overhead in terms of the number of shots. The other thing you see here, that increasing the number of shots, the overhead only gives you logarithmic gains. So there's kind of an optimal, in some sense, overhead that you'd want to use, which is sensible. You can plot these volume boosts for different values of x as a function of the accuracy you demand, and you can see that for high accuracies, you can get boost factors which are on the order of 1,000 or even more, depending on your x. Again, I just want to emphasize what is this boost factor. It means that you're able to run a quantum circuit with 1,000 more operations, 2-qubit gates, than you'd be able to run otherwise on the raw quantum computer with no error mitigation. Okay. Now, another important question, so when you want to ask yourself, okay, so is it actually useful to do error mitigation because of this exponential cost? You could worry that the whole premise of quantum computing is to give you an exponential speed up versus in some applications. But if you now have an exponential overhead in terms of the QPU time, it might wash away all the benefit of actually using a quantum computer because of this exponential runtime. But the difference is here that this exponential runtime has a very small number in the exponent, this infidelity, 1 or minus the fidelity, where the classical time scales exponentially with the number of qubits or with the volume of the circuit. So this leads actually to a very large, if you take these two scales, this leads to a very large polynomial speed up, whose power could be on the order of 1 over the infidelity, which is a very large number, for infidelities we already have today, right, on certain QPUs. And this very large power can actually lead to dramatic quantum advantages already on practical scales. Okay? So it's true that you cannot get an asymptotic exponential quantum advantage if you're using error mitigation, but you can certainly get a very, very large polynomial speed up. Okay, so now this was kind of a general overview of the benefits of using error mitigation. I want to kind of dive deeper into our specific product and method. And I first kind of want to maybe chart out the landscape of error mitigation, because there's many methods that have been proposed. But I think one way to make this chart is to just think about a one-dimensional line where you want to balance, on one hand, speed, and on the other hand, accuracy and reliability. So on this kind of one-dimensional axis, you've got, on one extreme, methods like zero-noise extrapolation, which are heuristic, but have quite good overhead in terms of the speed up. It's still exponential. Everything is still exponential. Here you just amplify the errors and try to extrapolate to zero noise, but there's no guarantee that this extrapolation would actually give you a good value. On the other hand, you have methods like probabilistic error cancellation, which under some assumptions, you can prove that they have no systematic errors. They give you an unbiased estimator, and they are completely reliable. However, they are very, very slow. Okay, their overhead is much, much more severe. And there are other methods that you can plot on this one-dimensional axis I will not discuss, but our software basically tries to balance these two extremes, somehow give you accurate and reliable results, but also with a manageable overhead. Okay, so now let me discuss a little bit the flow of the product itself and also kind of highlight some key innovations, which I'll dive deeper into following slides. So how does the workflow kind of from a bird's eye view, how does it start, how does it go? So the user's input is the quantum circuit he wants to run, or set of quantum circuits he wants to run, and the observables he wants to measure, and the accuracies at which he wants to measure these observables. This is a very important parameter, which is important for the runtime. And then once the job starts, the user specifies a specific QPU he wants to execute this on. And once the job starts, we first kind of do an initial characterization that kind of maps out the fidelities and the crosstalks between the different qubit pairs. And based on that, we could do something called kind of noise-aware translation, basically transpile the circuit into an optimal way on the QPU that would we reduce the overhead as much as possible just by basically doing this transpilation. Also based on this characterization, we then do error suppression, meaning trying to suppress any errors that are reversible and that can be eliminated with no overhead. This usually amounts to certain calibrations that we can do on the gates. And then we start the real heavy lifting. We start kind of a much more detailed and precise characterization of the actual operations needed for the specific circuit that the user input. And after we've done this characterization, we actually run the error mitigation job, which actually runs an ensemble of circuits. It's actually intertwined also with characterization circuits to keep track of drifts and fluctuations. And then at the end, we output the error-free results to the user. Now, if you think kind of about several key innovations I want to highlight that kind of allows both the accuracy and the efficiency, I'll discuss several of these. Is something we call multi-type quantum quasi-probability distributions, which allow us to actually get better scaling. Something we call active volume identification, which allows us to really minimize the numbers errors we're actually trying to mitigate and minimize the QPU time. There's a lot of optimization you can do in terms of runtime because different operations have different actual physical time for execution. And you can actually optimize the time on each QPU based on knowing on these time scales. Now, all QPUs of all modalities have drifts and fluctuations on all time scales, and it's crucial to track these fluctuations and these drifts, because otherwise, error mitigation, which runs jobs on several, on an interval of time, would actually be very susceptible to these drifts. I discussed this transpilation and also these calibrations. So after this is kind of very high level overview of the workflow. I'm not going to go over this code. Don't worry. This is just to show you that there's actually, an API behind this, and the job. This is just an example where the user sets the circuit and observables he wants to measure. He starts a job. Notice that there is this flag here. It's called empirical time estimation. I think this is a very important kind of feature that we're giving the user because of the time required to do error mitigation. It's crucial to know ahead of time, given a quantum circuit that you want to execute, how much time it would take to actually reach that accuracy. You don't want to start an error mitigation job that will run for a prohibitive amount of time and, take too much of your credits or something like that. So we're actually using a very short execution to get a very precise estimation of the total time it would take to reach the accuracy you require. And if this time we return, is too long, you might want to go back and try to optimize the circuit, think about the accuracy you want to get, and see what you can relax in order to actually decrease the QPU time. So, I think a big part of what we're trying to do when we're trying to kind of scale up our quantum algorithms is try to understand how much time to actually take to execute them. And this could give you an empirical estimate for this time with using a very, very short execution. So this is a very important feature in my opinion. And after you've obtained this time estimation and you're happy with this estimate, you can go ahead and run the job and proceed. There's several metrics which we output which would be maybe interesting to users. For example, the noisy results, the shot counts for mitigation and characterization, the fidelities of the gates and actual transpilations. And let me now show you kind of typical results. This is an experiment we did, kind of a large-scale experiment we did on an IBM Heron device. This experiment ran on 100 qubits out of this device, which were functioning well. In principle, this is something physicists call the kicked transverse field Ising model. If you don't know what it is, this is just kind of a hardware efficient circuit in the sense that it has layers of 2-qubit gates and single-qubit gates with some parameters for the 2-qubit gates. You see there are 2-qubit gates here, which we call RZZ, with some fraction and angle. So these are non-Clifford 2-qubit gates and also kind of non-Clifford single-qubit gates. We're plotting this as a function of the number of Trotter steps. Each Trotter steps is basically 3 of these, or 6 layers of CZs, if you want. This amounts to kind of a single Trotter step in this language. And you can see here the ideal values. These are this gray dashed line. This is the values we obtained using a simulation using tensor networks and belief propagation on 2 dimensions. This simulation actually starts becoming quite heavy already towards 8 steps. Not impossible, but starts to get demanding. And you can see here the results obtained using QESEM with these error bars. As I discussed, these are statistical error bars. All of these points are within the statistical error bar. You can see what you get from just running the noisy quantum computer as is. There is a big systematic error. We also did some kind of an attempt to execute the circuit using a highly optimized zero noise extrapolation method, and you see that indeed it gives you at some point a systematic error at the highest volumes. This is in fact this is the plot of the active volume of the circuit as a function of this number of steps, and we can also measure different observables, not only kind of single-site observables, but higher weight observables. Now, one important question is whether you're really using an unbiased method or not, or whether you're only remaining with statistical errors at the end that you can improve just by running for a longer time, or does your estimator actually have a bias? And here we've plotted a very large number of observables across all of these experiments. And we've plotted basically the renormalized z-score. This is telling you basically what is the value of the result based if you divide it by the error bar. And you see that all of these results provided by QESEM fall within this Gaussian behavior, which is what you expect from an unbiased result. Okay? Where if you try to use Z&E, you get a different histogram, which is shifted and showing you that you get a bias. This is a biased method. It has no guarantee to give you the correct result. Okay? So, we take great care in verifying that indeed all of our workflow ends up in unbiased results. Some kind of highlights I want to discuss. About our innovations. These are all described in our paper. If you compare, our method for doing quasi-probability decomposition to kind of the most standard way, which is called probabilistic error cancellation, then for the experts in probabilistic error cancellation, you can assume that the errors occur either before or after the operations, and by that you also insert the extra randomized gates. We're actually using a method which allows you to correct errors that also occur during the physical operation of the gate, and we're inserting gates before, after, and even replacing the gate itself. So it's a much more general method. And it allows you to obtain, first, deal with a much larger classes of errors, physical errors, but also to mitigate non-Clifford gates, which basically allows you to compress circuits and keep error mitigation, where standard PC is only compatible with Clifford gates. This is an example of our calibration. So the main errors in many QPUs are ZZ coherent errors, and it will be good to actually just correct them by calibration. And this is what we do. As you can see here, the kind of CDFs of the errors before and after our calibration. See, there's substantial gain that you can get just by calibrating the ZZ errors before you actually run. And also, as I discussed, we have a method for identifying the active volume of the circuit without actually simulating it. I won't go now into details, but if anybody's interested, I could go into more details. And we could actually then create candidates for these light cones and empirically measure their bias and kind of select the optimal light cone that kind of gives us the best bias versus statistical error. So this is a very important part in trying to speed up your error mitigation. So what's going on? All right. So here's another example. This is a VQE circuit that we've executed, and actually we used a very nice feature here where we parallelize this VQE circuit on the device. This specific VQE circuit is VQE circuit for the H2O molecule, and it uses kind of a modest number of qubits, which is 8. So then if you're using a smaller number of qubits than actually available qubits on the QPU, you can actually parallelize this execution and basically increase the, speed up your execution, because you're collecting now statistics from different regions in the device. But when you do that, you can run into a problem that, when you try to parallelize your execution, the fidelity degrades as you're using more and more qubits. So you need to find a parallelization that balances your need to, speed up the circuit and parallelize at the execution and parallelize. And on the other hand, by doing that, you're reducing the fidelity of the device. And we have a method for kind of, optimizing this. And this is the method here. You can see the selected regions of the device for this specific circuit. And the different instances, their average gives, very, very good result compared to the ideal value for the circuit. And again, compared to values we can obtain with Z and E, which are again biased here. So again, this is a feature that you can just apply just by adding a very small flag to your execution. This is a different VQE experiment we ran on IonQ, just to show you that this method is transferable and can work on different modalities of QPUs. And this was kind of an O2 molecule. And again, you can see that the ideal value of this ground state of this molecule versus our result here with this error bar, and what you would get if you try to run this circuit as is on the QPU. Now, we've been working with many partners and clients. Just to maybe flash a couple of these. So a group at DESI, this is a cyclotron research center in Germany, headed by Carl Jensen. We've been using QESEM for a variety of applications, including, studying quantum field theories in 2 dimensions, and also looking at velocity fields for computational fluid dynamics. The team at the Pacific Northwest National Laboratory used QESEM for their simulations of chemical system. And another nice example was by SoftBank, which were interested in quantum machine learning, and we're looking at the quantum kernel method. And they were basically computing this kernel matrix. This is the ideal value of the kernel matrix. The colors here are not great on this projector, but this is the ideal value for this kernel matrix. And you can see that if you try to run this kernel matrix and measure it on the QPU, you lose a lot of the interesting features, the important features for this kernel matrix, and the predictability becomes much worse. Where if you use QESEM, you actually can get back all of the, all of the features of this ideal matrix for very high accuracy. For this, to get this matrix, you actually need to run a very, very large ensemble of circuits. And we have a way to basically run a large set of parameterized circuits in a single execution, which both increases the efficiency, reduces the characterization time, and also increases the robustness to drifts. So let me kind of rush quickly through this. I want to kind of highlight this possibility to do what we call quantum-enhanced MPO computation. So I'm guessing many of you know what MPOs are. This is a way to represent certain classes of quantum states with very high efficiency. Instead of kind of using, here I'm thinking about operators. So instead of thinking about exponentially large number of parameters for to the end, I would use kind of an MPO with one dimension x or chi, and I'll need basically a linear number of parameters here, linear number of qubits, and the computation efficiency for classical computing would be more or less chi squared times the number of qubits. And this is a very widely used in physics, chemistry, also actually in classical machine learning. So what we're offering here is to do a quantum-enhanced MPO computation, basically to take this classical data structure, this MPO. It could be a result of a simulation, a classical simulation, or just a data set, and apply a quantum circuit on top of this MPO. We've used this to run basically a hybrid job, which we can think about as a circuit cutting. We take a quantum circuit, we cut it into a quantum part and the classical part. On the classical part, we backpropagate an observable using classical resources. Here we did the collaboration with RIKEN, which used their Fugaku supercomputer. And on the quantum part, we forward propagate the state. And we basically measure the back-propagated MPO on the forward-propagated state. You can see here the excellent results. Again, gray points are the ideal values. The red, as before, are what you would get just if you try to run the circuit on the QPU. And the blue points are the results of QESEM. This was an experiment run on 75 qubits. And you can see that in this experiment, if you try to do it quantum only using error mitigation, you'd be only able to reach about 16 Trotter steps, where with this method, you're really able to expand to 25 Trotter steps. But this is just an example of one possible application, maybe the most simple one, just to cut a circuit into two parts. You can replace this kind of part of the circuit by a completely different classical simulation or a completely different functionality here. And if you really think about the efficiency of the method and how it scales, you can actually compare the resources you would need if you start with an MPO with a very large one dimension, kind of pushing the limits of what you can do on classical computing. You can take a one dimension of around 10 to the 4. This is kind of one of the largest sizes, I think, reported, and try to push more this kind of quantum evolution. And kind of we did some estimates. For example, for this NVIDIA Grace Hopper chip, I think is one of the most advanced chips available today. And you can see that if you start with this one dimension, you try to push further this type of evolution, you get into really prohibitive classical runtimes, where if you use this kind of circuit cutting method I've just described, you do have a classical runtime that you need to pay an entry price, because you need to do some number crunching before you can actually apply the classical circuit. But once you do that, the classical runtimes are together with the classical ones, give you a much better scaling, and in fact, possibility to do things that are completely unfeasible only with the classical resources. So basically, anytime you have a classical computer, this method allows you to append the quantum computer on top and actually squeeze some more juice of what you can do. And just before I end, so I mentioned the possibility to combine error mitigation and error correction. And you can see this example in the slide. We have a method where we're going to publish soon, which is called syndrome of rare logical error mitigation, which kind of optimizes the use of combining error mitigation and error correction. You can plot here the circuit volume boost you can get with this method, assuming you're using some level of error correction. Again, you get this very high circuit volume boost, which diverges as a 1 over epsilon, 1 over the accuracy. And in fact, this specific method gives you much better performance than just doing logical error mitigation kind of in a very naive way. So I think this is an important boost. Even once we're able to start doing error correction, you can look at an example. You can take the code that IBM is pushing now as one of their kind of contenders for kind of a scalable architecture. And with this code, if you take an infidelity of 10 to the minus 3 on the gates, the largest volume you'll be able to reach is slightly less than 1 million gates, which kind of puts you only on the boundary of what we call the mega Q regime. If you're using error mitigation, you could basically increase that by a factor of 100 or even more, up to 1,000, and kind of go way beyond and deep into this mega Q regime. And so just one more note, you can look at these figures and think about the QPU time versus the active volume of your circuit. And you can see that already with fidelities that you have today, we're very close at the point of having quantum advantage, of having executing accurately quantum circuits that are not feasible for classical computation. Thank you.
Thank you.